Welcome to this 14th lecture of this lecture series. In previous lecture, we have seen that if we have a potentially unstable transistor device, then how to choose my gamma L and gamma S to make it conditionally stable. Now, that time we raised the question that can we just from the S parameters can we determine whether we need to draw the stability circles or not. The answer is fortunately yes. People have devised some analytic test based on S parameters to test whether the device is unconditionally stable or not. If the device is unconditionally stable, you go ahead with your actual amplifier design, you need not worry about the stability. If the test fails, then you need to locate or draw the stability circles on the Smith chart and then determine the ranges from where you will have to choose your gamma S and gamma L value, and then you can proceed to amplifier design. So, we will see that test. That test is called, there are two tests, anyone you can do, they are called Rollett's test or Rollett's stability criteria. So, Rolle, he have found out a parameter called K, which is given by 1 minus S11 square minus S22 square plus delta square. Delta is the determinant of the S matrix to S12 S21. Such a simple parameter he proved, it can be easily proved, but that is you can see in books it is given, but that is not so important for the design. So, you know that if this K value, you see everything here depends on S parameter values, S parameters. So, you can find out K, and if this K is greater than 1 as well as if delta, which is nothing but if you see the S matrix, it is S11 S22 minus S12 S21, this magnitude, that means this is a real number. If this is less than 1, then we say that this Rolle's test then passes you and device transistor is unconditionally stable. That means you can choose any passive load impedance and source impedance, and still you need not worry, your device won't go into oscillation. This is called Rollett's test. Another test, here are two conditions that should be simultaneously satisfied. Another test, this is also sometimes called K beta test, K delta test. This is called Rolle's constant or Rolle's constant K. Another test is called mu test. It depends on, here you have K and delta both you have to test, but mu test is an improvement of that. It is recently people have found out, and this test says that you test this parameter mu. Mu is given by 1 minus S11 square by S22 minus delta S11 star plus S12 S21. So, this mu is given by this, here also you see this is a real number, and if this is greater than 1, then we can again say that device is unconditionally stable. So, any one of these tests you can do, basically from these equations after manipulation you can have this mu parameter. So, this is nothing new, but people have made it more convenient. So, if you test this, you can say, if not, if it fails this test, any of these tests, if it fails, then you need to draw the stability circles. Okay. So, let us see an example of this. See in the rest part of this, we will see, already we have seen stability criteria, unconditionally stable devices. Then we will see an example that if we get a conditionally stable devices, how that can be, if we have an potentially unstable device, how we can make conditionally stable amplifier design from that. So, this is from Gonzalez book, I have already referred that book. So, in page 100 of my edition, this problem is given that suppose S parameter of a transistor at 800 megahertz is given like this. These are the values given. First determine the stability, then if potentially unstable, then draw stability circles and then show how resistive loading can stabilize the transistor. We see this is a new thing, we will discuss that with the example. So, you see we will test Rolle's test. So, K we can calculate and delta we can calculate. So, it turns out that K is equal to 0.547 and delta is 0.504 and with a phase of this. Now, since K is equal to 1, so we see that it fails Rolle's test. So, the transistor is potentially unstable at 800 megahertz, because we know that unconditional stability requires K is greater than 1 and magnitude of delta is less than 1. So, it has failed there. So, though magnitude of delta is less than 1, but K is less than 1. So, it is potentially unstable. Also in the mu test, if you do that, you see the value turns out to be 0.85, which is less than 1, but we know that mu needs to be greater than 1 for unconditionally stable. So, it says that stability checking, analytic stability checking indicates that this is a potential unstable device. So, if we want to use this device, we need to find out or plot stability circles and then determine what are the ranges of load impedance and source impedance, so that we can make it stable amplifier. So, you see that first we have done input source stability input stability circle, CS expressions I have already given. So, those are all I can calculate, that center will be 1.79. You know, Smith chart has a radius of 1. So, the center falls outside Smith chart, that you see that center is here, it is outside Smith chart and 1.79. So, this distance is 1.79 and this angle that it makes is 120 degree. So, it is here and RS is 1.04. So, partially you see this is 1.79, the radius is 1.04. So, it will partially intersect the Smith chart. So, it has intersects the Smith chart. Then we need to determine which one is the stable zone. So, values of tau s for which gamma out is equal to 1. This is the input stability circle. It is the border of stable and unstable region. Then as I said, assume that ZS is equal to 50 ohm. So, gamma s is equal to 0. So, gamma out magnitude turns out to be S22 magnitude, but what was STT magnitude? You see S22 magnitude is 0.8. So, it is less than 1. So, S22 magnitude is 0.8. So, I know that this inputs this the portion of Smith chart that is containing center, that is the stable region. We have marked the stable region with this black shading and this is the unstable region. So, I will have to choose the gamma s from here. Similarly, we draw output stability circle. This is the center, again outside, the center is outside the Smith chart and this time 48 degree. So, this angle is 48 degree and you see the radius is 0.45. So, 1.3 minus 0.45. So, there will be intersection. This red line is that locus of that circle, a part of that circular arc. And so, again here we can check that when we will simply match the load side, then gamma in becomes point S11 magnitude, and S11 magnitude is in this case is 0.65. So, we can again say that this input side is the stable one. So, from this stable region we will have to choose our gamma L. So, now how we can do that, and also you see that if we want to give resistive loading, suppose this is my input stability circle, this is my output stability circle. Now, I see all these constant resistance things. So, the one that is tangent to this input stability circle. So, there I can choose the corresponding, this is the constant resistance circle of resistance value, normalized resistance value 0.18. So, I can put in the, since this is input circle. So, if I put this value, you see I am further off here, and so I can add a 0.18 normalized resistance. So, with a 50 ohm characteristic impedance, the value is here you see 9 ohm. So, I can add in the source side, that means with the base of the transistor I can add a 9 ohm resistance. Similarly, from the output stability circle I can find out the tangent circle and find out that this is a constant resistance circle, this blue one of 0.58. So, upon unnormalizing I see that 29 ohm. So, at the load side I can put a 29 ohm series resistance, and that will make the whole thing stable. So, it will stabilize the transistor. Now, sometimes at the output you want to have parallel loading. So, that we can see that this 0.58, if I just change it to the, or this I can find out what is this point's admittance impedance, and I change it, that becomes 0.11. So, from that 0.11, you know, for admittance conductances I need to divide it. So, 500 ohm. So, instead of that previous case where I had, you see that previous case I have given a 29 ohm series resistance, instead I can also give a 500 ohm parallel resistance in the load side, and that will also stabilize the transistor. So, by this resistive loading you can add, but obviously this will change the overall S parameter or overall the gain condition. So, we need to check that whether this is true. So, we can do this, that the series resistance that we have had or shunt resistance that we have had, we can find the ABCD parameter. As you can see, that this one, this is a shunt element. So, it is in, so if I know the ABCD of this, because I know the S parameter of this transistor, so I can easily find out what is the ABCD parameter of this, then I can find out this shunt element, what is the ABCD parameter. I can multiply this to ABCD parameter to find out the resistively loaded transistors ABCD parameter. From that I can go to again S parameter back, composite S parameter, and from that I can again see whether this resistive loading has stabilized that, because that this composite thing now needs to pass the Rayleigh stability criteria or mu test. So, that we will be doing, these are the formulas you can refer to. So, you can find out that when I have a series Z, I know this is the ABCD parameter. So, overall ABCD parameter in that case will be this. Similarly, for the shunt one I will have this, because this, then in shunt with that I have this. So, overall ABCD parameters comes out to be this. These are the transistor ABCD values, and then I can reconvert after doing this multiplication, I can reconvert it to overall S parameter. Overall S parameter is this. You see stability factor, so I can calculate the Rolle's factor, that turns out to be 1. So, you see, and beta magnitude, that is 0.409. So, I know that I have passed the test. So, above network is unconditionally stable at 800 megahertz. So, this is the way by which if I have an potentially unstable device, still with loading, proper loading from finding from Smith chart, I can make it conditionally stable. Okay. So, after that we will try to now do the actual. So, this is stability checking. After that we will see the conjugate matching. So, design of amplifier, with conjugate matching, because that is our actual aim. So, we will do that design with conjugate matching, and you see that I have now made the stability analysis. I have chosen gamma S and gamma L ranges, etc. Now, if we refer to our original diagram, in previous class we have said that finally under conjugate matching I will have a source, then I will have a conjugately matched thing, then an input matching network, this is conjugate impedance matching. This will be connected to the transistor, and then I will have output matching network, and then it will be finally looking at Z0. So, I know that actual ZL is different, but with output matching it will appear as Z0. Similarly, actual source impedance is ZS, but I can with input matching network I can make it. And that day we have also seen that the transducer power gain, that comprises of these, that you can say this generally we call ZS, then this the transistor side that we call Z0, and this is ZL, and this Z0 is typically is not in our hand, because transistor manufacturer, he has made the transistor, that transistor is giving me some S21 values. So, we know that typically this Z0 is given by S21 square. Now, an microwave designer, amplifier designer, his job is to now design input matching network and output matching network, so that I will choose my proper gamma L and gamma J, gamma S and gamma L, so that the ZS that will appear as Z0 here to the source. Similarly, the ZL with this output here was ZL, but with this output matching network it will as Z0, then it will be conjugately matched. Now, what is conjugate matching? That time we have seen that gamma in is nothing but gamma S star, and simultaneously, because in general for any transistor, unless and until we do unilateral assumption. So, for a bilateral transistor, S12 and S21 are different values. S21, so in that case when I have a bilateral transistor, this gamma in, that is a function of gamma L, and gamma out is a function of gamma S. So, together simultaneously the input and output should be matched for conjugate matching, and conjugate matching says that you choose gamma in is equal to gamma S star and gamma out is equal to gamma L star, so that you become a conjugate match and you get maximum power transfer. So, this is already given by the device manufacturer. So, our job is to now design for this ZS and this input matching network and output matching network, so that I can get maximum of these ZS and this ZL. Now, last time we have found out the expressions for this ZS. So, that expression I am writing again, that, or before that, this GT, we have also found out the expression for GT in terms of S parameters and gamma S, gamma L. Now, under conjugate match, that GT will be maximized, transducer power gain is maximized, and that equation, obviously we are assuming that this input matching network and output matching network are lossless. We have seen in the basic building blocks of microwave engineering, those NPTEL lectures, that how to design lossless input matching network and output matching network. Those are not lumped elements, L section lumped elements, they are used for lower frequencies, but at high microwave frequencies you need to have transmission lines and transmission line stubs to design lossless input matching network. So, that GT max will become 1 minus this expression we have already found last time, S21 square and 1 minus gamma L square by 1 minus S22 gamma L square. So, with our this nomenclature GS, G naught, GL, basically this I can say is my GS maximum, this is my GL maximum. So, now we have enforced this condition. So, again start from these basic conditions, that I have gamma in is equal to S11 plus S12 S21 gamma L by 1 minus S22 gamma L, gamma out is equal to S22 plus S12 S21 gamma S by 1 minus S11 gamma S. And you see, as I am always saying, that gamma in is a function of gamma L and also S parameters of the device, gamma out is a function of gamma S and S parameters of the device. Now, for conjugate matching, I know that this gamma n, so this is general. Now, conjugate matching, that time I will make this choice that this gamma in I will choose as gamma S star. So, gamma S star is S11 plus S12 S21 gamma L by 1 minus S22 gamma L, and gamma L star, that will be S22 plus S12 S21 gamma S by 1 minus S11 gamma S. So, you see that by conjugate matching I have replaced gamma in and gamma out with their appropriate gamma S and gamma L values. So, you see this is two equations, here all S parameters are known, I have two unknowns, two equations. So, I can write two equation, two unknowns. What are the unknowns? Gamma S and gamma L. So, I can solve for that. Let us solve first for gamma S. From this equation, if I solve for gamma S, then gamma S becomes something like this. You see, just simple manipulation, but obviously complex number manipulation. So, that part you need to take care, but otherwise it is trivial. and this becomes everyone do it, right, take a pen and paper and do it. So, this is a you see solving. So, I think I should write it solving for gamma s from these two equations, two unknowns. So, I can solve for gamma s, that means basically you replace all gamma L values and you get a quadratic equation in gamma s. So, gamma s, you see this is some complex number, this is a real number, this is the coefficients here, this is a complex number, this is a real number, this is again a complex number. So, we know the solution of quadratic equation, we can find the roots, that will be given by if I call that if this one, this whole thing I call minus B1, this one I call A1 and this one I call C1. So, I know gamma s I can write, remember instead of B1 I have taken minus B1. So, gamma s can be written as B1 plus minus root over B1 square minus 4. You see just simple manipulation, you write it, you know this is Siddharthacharya's formula, Indian contribution. So, 2 C1, only thing here is this A1 and C1 they are complex numbers, but Siddharthacharya's formula still holds. Now, this what is then I should write what is B1 values, B1 is, since this is minus B1. So, B1 will be 1 minus 1 plus S11 square minus S22 square minus gamma magnitude square, and C1 we will see A1 and C1 they will just complex conjugate of each other. So, I need not write it as, so A1 is not present in this because actually A1 is complex conjugate of C1, that is why we are getting a 4 C1 magnitude square, and C1 will be this one S11 minus delta S22 star. Okay. So, with this now this will have solutions provided this part, this B1 square minus 4 C1 square. You see B1 minus B1 is a real number. So, B1 is also a real number. So, this and this is also a real number. If this is greater than 0, then only this will have a solution. So, people have found out that okay, this it can be shown. So, first this will have a solution, and once that solution is there, we can easily, because all these are known quantities, you see there are no unknowns, no gamma L is involved in this solution. In this only I need to know the S parameter values, delta is also dependent on S parameter. So, I can immediately solve for this. The root will exist, root will have a physical existence if this is satisfied. Similarly, if I solve for gamma L, solving for gamma L, we get another equation, quadratic equation, and that solution is, we call it 2 or B2 plus minus root over B2 square minus 4 C2 square by 2 C2, where B2 is given by 1 plus S22 square minus S11 square minus delta square, and C2 is S22 minus delta S11 star. Now, again here it will have solution if B2 square minus 4 C2 square that is greater than 0. So, I got two such conditions B 1 square minus 4 C 1 square greater than 0 and B 2 square minus 4 C 2 square plus 0, where B 1 B 2 C 1 C 2 are these. People have shown that these conditions enforcing these two simultaneously, that B 1 square minus 4 C 1 square greater than 0 and B 2 square minus 4 magnitude C 2 square greater than 0, this is equivalent to that criteria that K, which was Rolle's stability factor, K greater than 1 and delta less than 1. So, that means, what is this mean? That if I have made a conditionally stable amplifier, then these things are automatically satisfied, and so gamma s and gamma l are values. So, I can always find the gamma s and gamma n value, and when the roots are chosen like this, then we can maximize G T max, and that is given by S 21 by S 12 to K minus root over K square minus 1. So, this gain, that maximum gain for conjugate matching, that sometimes is also called matched gain. Actually, more scientifically it should be called conjugately matched gain, because there is also a simple match case. Now, if we have devices for whom, you see, if we have devices for whom K is less than 1, then conjugate matching is not possible. Then we have, but what we can do, we can enforce K is equal to 1, that is the maximum possible gain of maximum possible transducer gain. So, that is called G maximum stable gain. This name is maximum stable gain, and that is given by simply S 21 by S 12. So, if you failed, your device have failed the Rolle's test, then also you can make proper choice from this, and that time you will get a gain of S 21 by S 12. Usually in any practical transistor device, S 21 is a quite high value and S 12 is a low value. So, you get good amount of gain even from a device without this. Now, this becomes further simplified if we do it for unilateral case. That time the input and output, their coupling, that means gamma in depends on gamma L, that is not there for unilateral case. You know, unilateral means S 12 is 0 or approximately 0. Under that case, we know that gamma S under becomes that means S 11 star, and gamma L becomes S 22 star. So, you see, with this formula we can write that G T unilateral maximum gain possible, that will be given by simply 1 minus S 11 square, instead of 1 minus those other complications, S 21 square and 1 minus S 22 square. So, this for unilateral case, which many times we will see that we can assume this, and that time we can achieve a transducer gain maximum like this. For unilateral case, design is much simpler. So, I have chalked out all the possibilities. We will see, since this lecture does not have any more time, in the next lecture we will see a conjugate match design as an example. Thank you.